Hello, my name is Alexis Daniele, and welcome to my presentation on unit testing with JUnit. Let's start with the basics. What is unit testing? Unit testing is the process of testing small, isolated parts of a program, usually individual methods, to make sure they work as expected. Instead of waiting to test everything at once, we test each part as we go. This helps us catch bugs early and write cleaner, more reliable code. Why use JUnit? JUnit is a well-known testing framework built for Java. It's used to create unit tests that are quick to write and easy to run. JUnit allows us to automate test execution, check if the actual output matches what we expect, and easily connects testing into our development tools, especially in IDEs like IntelliJ and NetBeans. How does unit testing help with programming? Writing tests encourages modular programming, which means breaking your code into small testable pieces. That makes the code easier to manage, update, and reuse. Why would early testing be important? It helps prevent bugs. It's much easier to fix a problem right after it's written than to find later when it affects more code. Before we dive in, here's a quick overview of what we'll be covering in this presentation. First, assertions. We'll start by learning what assertions are and how we use them in JUnit to check if our code behaves the way it should. Assertions are the core of unit testing. They let us compare expected and actual results. Next, we're going to look at exception testing. After that, we'll talk about how to test code that's supposed to handle errors, like dividing by zero or trying to access something that doesn't exist. We'll learn how to write tests that expect exceptions and make sure our program handles them correctly. Then, we'll look at test class and suites. We'll look at how to structure our tests and to organize classes and group them into suites. This becomes really helpful when your project grows and you want to run related tests together. And finally, we'll look at the best practices. We'll end by going over some simple but powerful habits for writing clear, reliable, and scalable tests based on expert advice from sources like Marvin Fowler and the Clean Code Talk. By the end of this presentation, you'll have a solid understanding of unit testing with JUnit, from writing your first test to organizing and scaling your testing across an entire project. Now let's talk about why unit testing matters and the benefits it brings across the development process. First, it provides confidence that code works. When we write tests, we're confirming that each part of the program does what it's supposed to do. Passing tests gives us peace of mind that our logic is solid, and if something breaks, we'll know exactly where. Second, it provides documentation. Your tests act like live examples of how your code is meant to work. If someone new looks at your project, or even future you, the tests show what input were expected and what output should happen. Third, it prevents regression. Regression happens when a new change accidentally breaks old working code. With unit tests in place, we can usually detect if something that used to work suddenly fails before it gets released. Fourth, it speeds up development. Even though writing tests takes some time up front, it saves time in the long run. Instead of manually checking your work or debugging unknown issues, your tests catch problems early and make fixing them faster. Finally, it reduces manual verification. Once tests are written, you don't have to keep running your code and checking output manually. JUnit runs the tests for you consistently and automatically, so you can focus on writing better code. Now, let's look at where the unit testing fits in compared to other types of software testing. Test isolated functionality. This means we're testing one part of the program, like a single method or class, to make sure it works on its own without relying on the rest of the system. System and acceptance testing, or test overall application. These tests come later in the process. Instead of checking one small part, they focus on the entire system or full user experience, like logging in, submitting forms, or completing a workflow. Because we're testing smaller pieces, unit tests run quickly. They help us find problems early and are great for giving quick feedback while coding. Systems and acceptance tests run in pre-produced environments. These are usually run in a staging or test environment that mirrors the final version of the app just before deployment. Let's take a closer look at what JUnit offers and how it fits into the testing in Java. JUnit gives us all the basic tools we need to write and run unit tests in Java. We use annotations like test to define test methods and use assertions to compare expected and actual results. Localizes defects. If a test fails, JUnit shows exactly what went wrong, including the line number, what we expected, and what we actually got. This makes debugging faster because we know right where the problem is. Before we can use JUnit, we need to add it to our project. That might mean adding it through a build tool like Maven or making sure it's supported in our IDE. Once it's set up, we can start writing and running tests easily. It's also easy to run and review. Running JUnit tests are simple. Most IDEs let you run them with one click and the results are clearly marked. Green for pass, red for fail. This makes testing part of your regular workflow. Let's go over what a basic JUnit test looks like and how it's structured. Every test method in JUnit is marked with an @test annotation. This tells JUnit that the method is a test and should be executed when tests are run. Inside the test method, we call the method from our program that we want to test, like a calculator's add or divide function. We use assertions to check the result from the method and make sure it is what we expect. For example, we might write assert equals parentheses 5 add 2 comma 3 close parentheses, checking that adding 2 and 3 give us 5. These tests should always give the same result when run multiple times with the same input. That's what makes them reliable and trustworthy. Once written, the test runs automatically with no manual work needed. JUnit handles the execution, checks the results, and tells us what passed or failed. Let's talk about how to name and organize your tests so they're easy to manage and understand, both for you and for anyone else working on the code. When naming your test classes, it's common to name them after the class that they're testing, followed by the word test. For example, if you have a class called calculator, your test class would be calculator test. You also want to use descriptive method names. Test method names should clearly explain what the test is checking. For example, instead of just naming a test, test1, a better name would be test addition with positive numbers. This makes it obvious what the test does without needing to read the code inside. All your test files should go in a dedicated test folder. In most Java projects, this is something like an src /test or /java. Keeping test files separate from main code helps with organization and avoids confusion. Your test directory should follow the same structure as your main source code. If you have a package or folder for user features in the main code, you should have matching test folder with tests for the same feature. This makes it easier to find related tests and keep everything organized. Now, let's go over assertions, the foundation of unit testing in JUnit. What do assertions do? They let us check whether our code returns what we expected. If the result is right, the test passes. If not, it fails. How do assertions replace manual testing? Instead of running your code and manually checking the output, assertions do that for you. This makes your testing process automatic, fast, and consistent. Once written, assertions can be run as many times as you want, and they'll always check for the same expected result. That's what makes unit testing reliable over time. You can even add custom messages to your assertions. Adding a short message helps explain what the test was trying to do, especially if something goes wrong. Let's look at the most commonly used JUnit assertions and what they're for. Assert equals, parentheses expected, actual. This is used to check if two values are equal. It's one of the most common assertions. We use it to confirm that the method returned is what we expected. Assert true, parentheses condition. This passes only if the condition is true. It's useful when checking Boolean logic, like whether something is active, valid, or matches a rule. Assert false, parentheses condition. This does the opposite. It passes only if the condition is false. It's good for testing things like invalid input or failed checks. Objects assertions, such as assert same, parentheses object 1, object 2. These checked object identity, meaning whether two reference points to the same object or different ones. Each of these assertions help us test different conditions, and we'll often use a combination of them in the real-world setting. Now let's talk about what you actually see when you run JUnit tests and how to read the results. When everything works as expected, JUnit shows a green bar. That means all your assertions passed and your code behaved correctly. A red bar means your test failed. If something goes wrong, the green bar will turn red. This tells you one or more of your tests failed, and JUnit gives you details so you can find the issue fast. JUnit also highlights exactly where the test failed, including the file name, method, and line number. Different types of tests work, and more importantly, why we need to distinguish between them. First, unit versus functional versus integration testing. Unit tests focus on testing isolated components, typically small functions or methods written by developers. The goal is to make sure that each piece works as expected on its own. Integration tests go a level higher. These validate how different parts of the system work together. For example, how two modules interact or whether a service connects to the right database. Functional tests simulate a user's perspective, like logging into a site or submitting a form, and help us confirm that the system behaves as expected end to end. Why do we distinguish testing types? Each level catches different bugs. Unit tests are great for catching logic errors early. Integration tests help uncover issues with communication between parts of the system. Functional tests catch user-facing problems. Unit tests are cheaper and faster to run, but less broad. Functional tests take more time and resources, but they provide higher level confidence. This brings us to the test pyramid model. At the base, we have unit testing. These are fast and run in large numbers. The middle layer is integration testing, which is slower but done less frequently. At the top, we have functional testing. They're slowest and cost the most, but offer high ROI when it comes to catching critical bugs. Now, let's talk about JUnit 5, the latest major version of the JUnit framework. JUnit 5 brings a more modern, modular approach to unit testing in Java. It's made up of three main components: Platform, which serves as the test engine interface; Jupyter, the new programming and extension model for writing tests and extensions; and Vintage, which provides backward compatibility with the older JUnit 3 and 4 tests. This modular design means JUnit is more flexible and future-proof. It's easy to integrate into modern development workflow, whether you're using an IDE like IntelliJ, a build tool like Maven, or CI/CD tools. It also supports modern Java features like Lambda expressions and annotations, which make your tests more readable and expressive. That means you can write cleaner, more concise code that's easier to maintain. Why use JUnit 5 over earlier versions? Well, it's scalable, cleaner, and designed to work well with both legacy and modern Java. It gives developers more control, better extension mechanisms, and better integration with today's development practices. Let's go over how JUnit handles exceptions, a key part of building reliable defensive code. When you're testing your application, you want to make sure it behaves correctly, not just when things go right, but also when things go wrong. That's where exception testing comes in. JUnit provides several helpful annotations that support exception testing. Here are the main ones again. Test. This marks a method as a test case. It's required for every JUnit test method. Before each and after each. These handle any setup or cleanup that needs to be run before or after each test. Before all and after all. These run once for the whole test class and are typically used for shared resources or expensive operations. Display name. This gives your test a readable name in the reports. It's especially useful when sharing results or debugging. When it comes to testing exceptions, the main tool we use is assert throws. This tells JUnit to expect an exception. If the method doesn't throw one, the test fails. You can use this to verify your code handle errors properly. For instance, throwing an illegal argument exception when given a bad input. Some additional tools could be disabled, which is used to temporarily skip a test without deleting it. Nested, which is great for organizing related tests under the same structure. Or tag, which lets you group and filter tests easily. Now that we understand how to test for exceptions in theory, let's look at a practical example. We're going to walk through the sample test class that uses a calculator object. First, we use before each to initialize the calculator before each test. This ensures we're working with a clean instance every time. Next is the test itself. We mark it with @test and we use an assertion to check if the results are correct. We also include display name so the test shows a helpful message in the report. This line means we expect the result of 2 plus 3 to be 5. If it's anything else, the test will fail. Then we use after each to clean up, resetting the calculator to null after the test. Set up and clean up in a clean and repeatable way. It also highlights the value of using clear assertions and display names to make your test output more readable. Now, let's talk about test suites. A test suite is a collection of related tests that are grouped together to be run as a unit. Instead of running individual tests one at a time, a suite allows you to execute them all at once, which is efficient and ideal for CI/CD pipelines or regression testing. The types of software testing. Let's break down the four major types. There's unit testing. This is the foundation. We test individual components, like functions or classes, in isolation. Then there's integration testing. Here, we check that multiple components work together correctly. Think of APIs, services, or modules communicating properly. Then there's system testing. This tests the entire software system as a whole, from input to output, ensuring everything behaves as expected when fully integrated. Finally, there's acceptance testing. This is testing from the user's perspective, making sure the software does what it's supposed to before it's released. Now, these testing types can fall under different categories. There's static testing. This happens without running the code. Think of code reviews or walkthroughs. There's dynamic testing. This involves running the code and checking the outputs. Typical unit tests and UI tests fall here. There's manual testing, which is done by humans. Testers go through features and verify behavior. Or there's automated testing. These are scripted or framework based, like using JUnit for unit tests or Selenium for UI testing. So when we talk about test suites, we're talking about bundling these tests together, whether they're unit, integration, or others, to streamline how we check the health of our code base. Let's talk about one of the most critical aspects of testing, the output and feedback you get from your test. What is software testability? Testability refers to how easy it is to test a software system. The more testable your code is, the more confident you can be in its behavior, especially as a system grows and evolves. Good testability means fast feedback when something breaks, clear results from your test, and fewer bugs making it into production. In other words, highly testable software supports efficient development and continuous improvement. Why does it matter? Here's what makes it important. It improves maintenance. When your tests are easy to interpret, it's easier to fix issues quickly. It boosts developer and team confidence. You make changes without fear of breaking things. And it supports CI/CD pipelines. There are several core characteristics of a testable system. There's observability, which is what you can see happening internally when something fails. Controllability, your control in the inputs and environment to isolate behavior. Simplicity, how straightforward is your code or overly complex. The stability itself, are the results consistent over time? And its understandability, can someone new quickly understand what their code and tests are doing? These traits can be improved through modular design, detailed logging, and dependency injection, all of which make tests easier to write and trust. Now, let's shift focus and ask, what actually makes code hard to test? Because understanding that is the first step to writing better, more testable code. First, let's look at what makes code easy to test. Each test should cover just one behavior or function, avoiding bundling multiple checks into that one test. Make sure to use meaningful names. Make it obvious what's being tested just by looking at the tested method name. Make sure to focus on each assertion. Don't test multiple conditions at once. That makes it hard to tell what failed and why it failed. These small changes go a long way in making your code clearer and more organized. Avoid common pitfalls. Here's what usually goes wrong. Avoid if statements or loops inside tests. Tests should be straightforward, not mini programs. Don't rely on global shared state. This creates unexpected side effects and makes tests unreliable. Beware of flaky tests. These are tests that sometimes pass and sometimes fail for reasons unrelated to your code. Flaky tests are dangerous because they destroy trust in the test suite. Always aim for consistent reproducibility. Think of a good unit test as a living documentation. It should clearly describe what your code is supposed to do without needing a long explanation. It's like leaving behind a note that says this method should return X when given Y. Let's now go over some core principles of writing testable code using JUnit. These are the techniques that help us write clearer, more flexible tests that scale well as our code base grows. Use test or @test to mark test methods. Every JUnit test begins with the @test annotation. This tells JUnit this method is a test. Run it when executing the test suite. Without @test, your method won't be recognized as part of the test run. Add before each for setup. Before each is used to prepare a clean state before each test run. You typically initialize objects here. For example, creating a new calculator instance before every test method so they don't interfere with one another. This is essentially for test isolation, which ensures each test runs independently and won't be affected by leftover data from a previous one. Use assertions to validate behavior. Assertions are where the real testing happens. You're comparing what you expected versus what your method actually returned. The most common is assert equals, parentheses expected actual. As we've seen earlier, there are many assert true, assert false, assert null, and so on. Writing precise, focused assertions keep your test readable and trustworthy. Each test should verify one specific thing. If a test fails, you should instantly know what broke and why. Avoid testing multiple scenarios in the same method. That leads to confusion when something goes wrong. Okay, let's talk mocks, stubs, spies, and DI. In simple terms, DI is dependency injection. It is when you provide an object's dependencies from the outside instead of letting it create them itself. Why does that matter? Because if your class is responsible for creating its own dependencies, it becomes harder to test. You can't easily replace those components with simplified or controlled versions. But with DI, you can easily swap in fake or controlled versions of those dependencies, and that's where test doubles come in. Let's start with mocks. They simulate behavior and let you verify if something was called. Great for checking interaction. Then there's stubs. They return fixed responses for method calls, useful for skipping expensive logic like hitting a database. Spies are like mocks, but they track behavior of real objects, helpful when you want to watch what happens without fully replacing it. Then there's fakes, simple implementations, like an in-memory database used for testing. Why does it matter for DI? These test doubles only work well when you've written your code to accept dependencies from the outside, using interfaces or constructors instead of hard coding something inside your class. That's the heart of dependency injection, giving your code flexibility and control, which makes testing faster, cleaner, and less brittle. Now, let's talk about one of the most effective testing approaches in modern development, test-driven development, or TDD. TDD flips the traditional development process. Instead of writing code first and testing later, You write the test first before you even implement the feature. Let's move on to the TDD cycle. Red, green, refactor. Red is when a test fails. This tells you the feature doesn't exist yet. That's expected. If it's green, write just enough code to make the test pass. Don't overbuild. If it's refactor, that means clean up the code while keeping the test passing. Improve readability or design without changing behavior. This loop ensures that you never write untested code. Every feature is backed by a meaningful test, and you only build what's needed. Why would you use TDD? Because it improves code design. It gives you instant feedback and confidence in your code, and it builds up a full test suite as you code, not after the fact. TDD isn't just for critical systems, it's now used widely in agile development, DevOps pipelines, and anywhere teams want fast, safe iteration. Principles that extend beyond just writing tests. These are ideas that help you deliver quality software in the real world. Design with testing in mind. The best way to write testable code is to think about tests before you write your classes. Use clean architecture, write small independent modules, avoid global state and long chains of dependencies. When code is hard to test, it's often a sign that it needs to be refactored, not just for testing, but for better maintainability overall. Unit tests as design feedback. Unit tests aren't just about catching bugs. They tell you a lot about your code design. If something is hard to test, it might be doing too much or depending on too many things. TDD helps with this by forcing you to write tests first. You naturally break your system into smaller, cleaner components. Tests are part of your delivery pipeline. In modern software teams, unit tests are integrated directly into CI/CD pipelines. Every time code is pushed, tests are run automatically. If a test fails, the pipeline stops. That's why tests must be trustworthy, repeatable, and fast. Testing in the real world. In enterprise and production systems, teams rely heavily on tests to save, refactor, upgrade frameworks, or ship new features. Without them, every change becomes a risk. So testing is not just academic, it's a practical professional discipline that supports real delivery goals. These are the resources that I've used for my presentation. Here are some great resources to deepen your understanding that were utilized for the presentation. JUnit documentation, Clean Code by Robert C. Martin, Mockito framework, and Clean Code Talks from Google. Thank you so much for following along. Let's close with a few final thoughts on unit testing and a quick reminder. Why unit testing matters. We've seen that unit testing is about more than just checking if your code works. It helps catch bugs early, encourages better code structure, supports faster development and deployment, and builds confidence when working in a team or on a large code base. When done right, tests become an asset, not a burden. They speed you up rather than slowing you down. Thank you for your time. Thank you for your time, and this was my presentation. Wow. Thank you for your time, and this was my presentation on unit testing for software engineering.